So you created your Ruby class, which you're going to use with setIntersection, but setIntersection is not working the way you expect. In particular, when you intersect two sets with your new class, it's coming back empty. What do? Well, you can access the online documentation for Ruby, or you can use structured exploratory testing to find out the answers. We're going to use the latter. Now, I like to structure my exploratory test sessions by using a reachability graph. Every system has a reachability graph. It's important to note, however, that a reachability graph is not a causality graph. A reachability graph simply connects two states, in particular two abstract states, as we understand the system. I like to use reachability graphs to direct my testing, which prevents me from going off on a tangent and into the weeds, and actually directs my testing to make it faster. Not to be facetious, but we should consider our failed attempt at setIntersection as our first test. It provides invaluable feedback and direction for the rest of our exploratory test session. Even though we know that setIntersection does not use widget ==, here I'm just showing that reachability can actually go both ways. You can go from one state to the other and vice versa. I use the inference forms modus tollens and modus ponens to build accurate reachability graphs. An important technique to have as a developer is called triangulation. In testing, it's called oracles, and I particularly don't like that name because it enhances something that is very trivial. It's just a comparison with similar objects. In this case, we're going to triangulate with string objects to see if setIntersection also does not use their == method. Same as we did with widgets, we're going to create an inference with strings, and we're going to see if string == is used by setIntersection. This allows us to create a reachability graph that is accurate for all the objects we test with. Note also that we don't get any output from string subclass, in particular the method ==. By using modus tollens, we negate the hypothesis. Because of triangulation, we can be certain that setIntersection does not use the method == of any object. Here I show a very interesting aspect of the reachability graphs. We're actually building the reflexive transitive closure of the states of the system under test. This is why one state can reach any other state if there is a path in between. That's all reachability graphs represent. So we know that setIntersection is not using == methods. What is it using? For that, I'm going to check the Ruby documentation, not online, but via the IRB console. I'm just checking for methods that stand out. EQL is one of them, so I'll test it out. It's important to point out that knowledge about the system that we're testing is very critical. I know Ruby has the IRB console, and through that I can list all the public methods for the object class. Hence, I know something about the system under test. Now, to prepare for the next set of tests using the EQL method, I prepare the reachability graph. And I set the reachability of these two states as suspected. This reachability is the one I'll test. And using modus tollens and modus ponens, they will confirm or deny whether my hypothesis is true. Depending on the inference form used, we might not be able to infer anything, like in this case. It's very important to anchor, so to speak, in something that we can actually see, something we can confirm. Hence, we need modus ponens instead to confirm our argument. We place C3 as our hypothesis, which is something that we can see, something that we can test. And Q4, the conclusion, is something that we want to verify. Now I do the same thing for the widget.eql method. Note here though I have a bug in the reachability graph. Can you see it? In a few minutes I'll catch it and correct it. Don't worry. Now here we find something interesting. It seems like setIntersection is not using the EQL method of widget. So I have to negate the properties of these two particular abstract states. But how can this make sense? I mean, setIntersection uses the EQL method of one class, namely string subclass, but it doesn't use the EQL method of another class, widget in this case. That doesn't really make sense. And this gets a lot of people confused. This gets a lot of developers and testers alike confused. It's important to understand that all these nodes in the reachability graph are abstract states. We can abstract away or put in as much detail as we want. It might be the case that the reason for the apparent contradiction is because we either abstracted too much or because we have too much detail. Let's abstract away in this case and see what we get. And this is where reachability graphs really shine. Via certain patterns, in particular the bicycle pattern in this case, it tells us that we need an abstract state. We're missing an abstract state that's going to show us why we're getting this apparent contradiction. So by abstracting away some details, I find that the original assumption I made was that only one method was being used by setIntersection. That new abstract state shows me the bicycle pattern. Now using that new abstract state, I will enhance it a little bit, and I'm going to think now maybe setIntersection is using two methods. We'll see. We need to test to confirm. And this directs our testing. Here's what I noticed the bug in the reachability graph. So it should have been intersection of two sets containing widgets, not strings. We fixed that, and we're good to go. Now to find out which method is needed, I'm going to go through the same steps as before. Using my knowledge of the system, I'm going to check the public methods and see which one stands out. I see hash, I see name, I see that equal method, and several others. So I do preliminary tests with each one. And I find that hash is probably the most interesting one. So I'll use that. So it turns out that set intersection is actually using the EQL method and the hash method as well. This validates my assumption, and the inference will confirm it. I can now establish a new edge in my reachability graph and learn more about the system. I could stop here because I accomplished my goal of getting widgets to act correctly with set intersection. But just for fun, I'll triangulate with string subclass. Now doing a test with string subclass shows that for some reason hash is not used, at least not the hash of string subclass. So as I did before, I abstract away some irrelevant details. Once I abstract away, I get to an abstract state that shows again the bicycle pattern. Perhaps set intersection uses a hash and EQL method of member objects or its parents. That is something to investigate in another session. For now, I'll call it good because widgets are responding correctly to set intersection. The other beauty of reachability graphs is that I can leave a mark on the last state that I found interesting so that I know exactly where to take off, where to start from on my next session without losing any valuable information. One last thing though, reachability graphs are called like that because every state in the system under test is related somehow. There are states that are not related, that you can't reach from certain states. But for these, we need an underlying fundamental state that reaches all of them. That's what I'm writing here. This is the fundamental state. Widgets, sets, and string subclasses can be created. That's the most fundamental precondition. That's all for today. Happy testing!